Okay, so this will be an overview talk. In particular, we'll talk about spatial AI, and what we mean by that essentially is the ability to understand the world from sensors to assist both people and enable robots to interact with the world. Okay, and so you see some of the devices we're using there, similar to actually what Andy was showing. It's both robots, but also devices that people wear. They mostly leverage the same type of algorithms, the same type of perception capabilities, to then essentially build first geometric representations of the world, but also beyond that, semantics and also affordances. How, you know, it's not enough to know what the object is, it's also important to know how you interact with it, what you can do with it, and so on. So those are the things we'll look at. Here's our latest robot. It's actually a French robot. It has some kind of nice style. It's the first Poland kind of Ricci 2 robot that they've sold. So we have the serial number 001. Okay, so let me first show you a little video that kind of, you know, with HoloLens that kind of illustrated a little bit the type of things that...
This is work.
The type of things that you could do if you were, you know,
giving
with
eyes and ears
computer
to AI.
vision, with kind of this mixed reality
So the world
devices,
becomes your prompt,
how you could help
interface.
people. And also think a little bit of what's
This
needed
is
for it.
work. Working.
For these scenarios that
These
are
are
you know,
thoughts
envisioned,
Hey, Copilot.
you actually need
Plans
more than
populated.
just a
Copilot,
huge,
when was this
big
last recorded?
model that
Information
has
gathering.
kind of, you know, AGI level
Instructions guiding.
capability of understanding what's in
Schematics
front of it. You actually need, as you can
People
see here, you need memory.
Problem solving.
You need to be able to represent space, to remember
Copilot.
what's in
Hey,
space, what's where,
Copilot.
have a digital twin available that you can
Copilot.
kind of
This is
connect
confidence
to the
score.
actual device,
Eyes
know
wide.
how to connect, you know, how to
These are questions.
steer
I
particular
just
devices,
finished
etc.
Copilot. What's next?
And so one of the first things that's needed is actually to be able to continuously be localized. So as you kind of walk around through space, you need, on the what you see on the right there, you need an alignment also to a digital representation of the space, which in this case is just showing you kind of a visual representation, but think of all the digital information being anchored to that also, so you can access it. Now, if you want to build that, and so this is some of the work we did at Microsoft. If you want to actually be able to deploy these type of things, technologies in a practical way, you can kind of, you know, build kind of a map once and for all, and then always leverage that kind of perfect map of the world. You need essentially a system that can do this on the fly as a byproduct of just using the device and keep your maps up to date and kind of complement your maps. And if you enter a new space, start building a new map. And that's what you see here. Essentially, the devices, just to operate, already need to build these type of 3D representations within a session. They're very good at that. They do that with always-on sensors and so on. But what we did here was to move some of that data to the cloud and then merge it in the cloud in a kind of more comprehensive map that also has different levels of representations, including radio signals and other things that can help with localization. Here's kind of an example of this, you know, kind of more bit at scale. This was me walking around for a number of hours with one device actually, walking through multiple levels. So a 4-story building of maybe 100 meter by 100 meter on the Microsoft campus. HoloLens has also built in depth cameras. So you see, essentially, we got essentially every piece of furniture in the building was reconstructed. And by the time I was finished walking, the map was essentially fully optimized and kind of available. Here's the same kind of thing, more in industrial setting, which is mostly what we're targeting. So you see here, this is kind of in Switzerland, a kind of milk production kind of facility, or where they process kind of milk, reconstruct on multiple floors. Now, switching back to more the academic side, there's been a lot of work in recent years on NERS, neural radiance field, and Gaussian splatting. Now, as you see on the left, those methods actually start from posed images. So they don't solve the pose problem, but they're essentially starting from that and just fitting an appearance model to a collection of images. Under the hood, although there's been great kind of learning-based feed-forward methods, under the hood, most of those still use kind of the classical structural motion algorithms, and there's good reasons for that. We're still working on that, so this was done by Johannes Schönberger, developed ColMap, which is collection mapping. So it starts on a collection of images, builds up a kind of a graph relating all of the images, that can be matched together in a big graph. Then from that starts building up a sparser reconstruction in a sequential mode. So it starts assembling from somewhere in this graph and then kind of extends that. You can also then build a dense model on top of it. We keep working on this. Lots of contributions from many of the students and other people, students in my lab, and also Johannes and many other people continue really driving this project forward. Most recently, as now there's many devices have many cameras on them, we essentially extended it to natively be able to support these kind of camera rig systems and be both more efficient and more accurate with those. At the same time, we've also looked at it's been kind of a frustration to not be able to look at all the images together and have to kind of start from somewhere and then grow it, which has a number of disadvantages. However, global structural motion methods had struggled for a long time to be kind of robust and function well. In particular, because while rotation averaging here works really well in general, the same for translation averaging that people are trying to develop often failed, and the reason is that the rotation averaging is a well-conditioned problem, but the translation averaging, if you have 3 cameras along a line, the fact of averaging the translation means that you have a complete ambiguity of how that middle camera, let's say, relates to the 2 other cameras, as you're just looking for the direction to be consistent, but you would kind of need 3 view correspondences to kind of nail these type of situations. Anyway, so what we did was to do both once you've solved the rotations, you both solve the positions of the point and the cameras in one optimization, which is a much simpler one than if you've done the rotations. And that actually ended up working really well with the proper engineering. Here you see some of the results. So we start from random initializations, and you get these type of reconstructions. Now, many of you could say, well, we've seen things with VGT and other kind of methods recently that, on these kind of models here do also really, really well and show impressive results. That's true, but however, they would utterly fail on reconstructions like this here. So what's the difference? Here, if you look at this, you essentially only have one local scene. Okay, you have one object or one scene. So from one image to another image, there's essentially a direct relative pose, more or less, that you can observe. If you think back of this viewing graph that we had before, the viewing graph has a radius typically of 1 or 2 or something like that. So the radius of the viewing graph is what is from a particular point, from a particular image, how many steps do you have to take, over the graph to reach every other image? This has a little bit to do with what Andy was saying of how much do you need to distribute information around and how big is that graph that you have to propagate information over and so on. Okay, so transformers are really good at exchanging information, having attention when things are relatively close, but if you have a graph with very long kind of need to propagate information very far, then a transformer that maybe does, a finite number of steps, maybe 24 propagation steps, can just not propagate information very far. Okay. So we've been working on that. So this is a preview of work that we've been doing. First, we analyzed more in detail these viewing graph issues for all these kind of feed-forward methods. And essentially, when the viewing graph has a radius of 1, that means that from a certain camera, you can essentially reach every other camera. You have co-visibility, essentially. With almost every camera, things work really well, but it starts going downhill very, very fast as you get a larger graph. Okay? As an example, a reference here, this Lindenhof neighborhood that we solve very nicely with GLOMAP and related methods, classical structural motion methods. It is challenging, but it does work. Has a radius of 59. So that means that you have to hop 59 steps from somewhere in the middle, from the best central location. You have to do 59 steps of co-visibility to reach the edges of this reconstruction. Okay, and that's completely beyond the reach of these current feed-forward methods, both in terms of memory, as well as actually being able to propagate information that far and get a good reconstruction. So what we've worked on is essentially a method that combines the best of both worlds. And that's what we try to illustrate here. Many different benchmarks here. And so this is showing you how well different methods do on each of those benchmarks. Further out is better. And you kind of see the difference here between the some of the best feed-forward methods that we found. So the other methods performed less well. On this side, with then the more classical methods, this is GlowMap. GlowMap essentially performs on par with ColMap in general. So using either SIFT features or like plus like glue to match images, you see they do better in some directions, in particular in terms of accuracy. Typically when they are enough features, the feature-based methods work a lot better than feed-forward methods in terms of accuracy, but they fail in more challenging circumstances where there's less overlap between images, less features to be found in the scene. But we were able to develop a method that essentially works better in all situations, essentially by combining really both methods. So we use feed-forward methods to get kind of the local graph connectivity, kind of star-shaped local graph connectivity, and then assemble all of that using global motion averaging, and then combine both the classical SIFT tracks together with then virtual tracks, and the actual feed-forward tracks as well as virtual tracks that we extract from what we get from the feed-forward networks. And that way we get a best of both worlds kind of solution that outperforms all of the previous methods. Okay, some other methods in matching. So we've also tried to make things fast. So we did here for just matching two images. This is a bit older work, where essentially we have a kind of a best possible trade-off between how many image pairs per second we can treat together with the accuracy that we can reach. And it's a sparse transformer network essentially that's doing that. So like do, and it's doing this. The number of iterations that you do is essentially can be adaptive. Although in terms of efficiency, being adaptive is not always, if you do massive parallel things, it's not always the best thing. But anyways, you can actually choose how many steps you go, and easier problems that are quickly converged, you can stop. Harder problems, you can keep going deeper. Okay, then in terms of Gaussian splatting and so on, and actually leveraging all the feed-forward methods that have been developed, if you have a few images, as we heard also before, there's essentially both a lot of information that can be obtained from putting images in correspondences, building cost volumes, and so on. But at the same time, there's also nowadays networks that manage to get really, really good results already inference from single images here. From molecular depth, kind of qualitative molecular depth estimates. And so in this case, we combine both. So those have been our pre-trained networks. But then what we do is we can essentially refine them and do fully unsupervised pre-training. The idea here is because we're doing Gaussian splats, our goal is to render the best possible images. So if at the input we have a video sequence or collection of many images, we can pick some of them to build the representation from, and then use all the other ones to validate how well we're doing in our loss function, essentially. And so our loss function is an unsupervised one because we essentially start from known videos, of which we pick a few frames that generate a Gaussian splat, and then we essentially have the loss function to make sure that all the other frames are rendered as good as possible. Here's kind of an example of this at work, 6 images. From those 6 images, this whole video is generated. Okay, and so there's artifacts, but it actually works quite well. The previous one still needed the poses given. This is work where we actually have 2 images at input, both the relative pose and then the whole Gaussian splatting representation is essentially generated in a fully feed-forward method. And again, here it starts from existing networks and then essentially does an unsupervised refinement on the task of generating Gaussian splatting. Here also you see the examples. The first and the last frame of each of those videos was input, and the whole rest of the video is essentially output here. Kind of our latest work in this space was trying to see if we could somehow leverage the information, the understanding of how a scene looks like that's embedded in flow model or diffusion models to complement. So we start with a few very sparse scene of which we try to generate a reconstruction. Initially, we have a not so good reconstruction from that. But then based on that, we condition the generation of additional views that then somehow fill in the missing information or kind of hallucinate, or condition on what we already have. We can generate quite good images, which allows us to end up with a better reconstruction in the end by essentially extracting the information, regularizing in a sense based on information that's contained in diffusion models. Then doing Gaussian splatting in the wild is often challenging. So all the examples you saw before, you essentially would take a collection of images all at the same time, a few images, and then generate a Gaussian splatting from it. But in many cases, you might just try to do the same from a collection of images in the wild, like here with the Trevi fountain. With the challenge being that the illumination is going to be different in every image, and you have to deal with that. And also the fact that there will be occluders or kind of random spurious thing, like, for example, with the Trevi fountain, you have always the random tourist that took the picture is typically there, or their wife or partner or whatever are typically also in the picture. And so you would like to essentially build that, those things being abstracted away. And here you see some results of this. And building on that, we've also done some SLAM system based on that, and we have more ongoing work in that space. What we've always found important is also to set up strong benchmarks. This is ETH3D that's still actually used a lot. Our new benchmark is LAMAR, localization and mapping for AR, where we collect a lot of ground truth. We collected data sets over several years. Even actually observing in front of the ETH main building, there was construction, things like this. So lots of really interesting data captured in this, with a goal also to validate localization or construction, not only from single images, but more from streams of images, so sessions. Most of the data is essentially posed with respect to the ground truth within a centimeter. We've continued doing this work. We switched to the ARIA glasses, so we call it LAMARIA. Also here collected lots of data. Our goal was the previous benchmark had, building here, and this kind of area, the Lindenhof down here. But we decided that we wanted to have very long trajectories through this whole downtown Zurich. So this is many trajectories are several kilometers long. And we want to be able to validate drift of VIO methods and SLAM methods over these really long trajectories without doing the easy trick of just walking a huge loop and coming back and then just at the end check how much drift you've accumulated in the special setting of actually walking a 360 loop somehow. Okay, including also challenges where you actually in a vehicle and you see a lot of features that are the inside of the vehicle, and so that might confuse you, etc., etc. So. And we've actually noticed there that the state of the art was really, the academic state of the art was really struggling. So this is something where we really wanted to push things. You will see it's actually not perfect, this video visualizing one of those trajectories. We're actually super accurate. We're essentially within a centimeter based on those ground control points and everything. But Google Earth isn't. So Google Earth is actually several meters off in many places. And that's actually the misalignment you see here. This is known. It's like 4 to 10 meters off often. Also more in kind of emergency scenarios and cross-device. Collected lots of data there. That's a crocodile data set where you see here actually all the different platforms. The key between those different platforms, not only different sensors, but also really different viewpoints. This robot has cameras down here. If you wear something, it's up here. If it's at a wearable, it's more up here. And then, of course, drones, fly kind of anywhere. Okay, so let me switch to now the semantic side of things. So this was the first work we did in that space. This was Song Yu Peng, and it was done in collaboration with Google. It was actually his internship at Google. And so the idea was to extend CLIP here that, this is the text encoder for CLIP and the image encoder for CLIP, to extend that with a 3D encoder. Okay, so this is kind of frozen, this is CLIP. We extended that essentially on the Matterport data set that has many indoor data sets. We essentially looked at the images, got clip descriptors from that, and then wanted to transfer that and generate directly from the 3D point cloud through a point cloud kind of encoder here, a vector that is as aligned as possible to the image vector, which then by transitivity we hope is aligned to the word vector, right? And once we've done that, when we have a new model coming in, we will essentially process it and generate for every point there, both on the texture images as well as on the 3D point cloud, some embeddings, an ensemble of embeddings, and then essentially we can start asking queries, fill in a query, floor, and then it will generate here what a floor vector looks like and correlate that with all the points, and then it shows you here the most relevant points that it finds. And the nice thing is you can do all kinds of things like classes of objects, more generic or more specific classes, but it's fully open vocabulary. So see here, so teacups, and then Snoopy, like a very specific object. It turns out there's one over there. And then, but then what's interesting is you can also ask other things like affordances, like where can I sit? And then we'll highlight all the places that make sense for sitting. All materials, and then it will find you those places and so on. Right? So it's actually really, really kind of interesting. We've then also done that on at object instances using Mass3D to detect instances and then essentially attach vectors instance per instance where you can really choose kind of the right imaging image data to kind of that's aligned with the bounding box of the object, etc. That was kind of the Mass3D itself was actually trained on specific types of classes and on specific sizes of objects. We've extended that to Segment 3D where we try to leverage SAM, that's a 2D model, to kind of help us also do segmentation in 3D. I won't go into detail here, but it essentially allows us to capture objects at different sizes, also parts of objects and so on. Our latest work in this space is essentially this 3D mood here, which is from an image plus a text query, it will essentially generate 3D bounding boxes for all the objects of interest in that image, as you see here, and it's fully open vocabulary. But of course, you are asking, about specific classes, and then it finds you the boxes that corresponds to those classes. Then also here a little bit in terms of image, like scene representations. Here's kind of one example of some of the recent work we do that's kind of both combining what people and robots doing things. And we essentially build up a scene graph, which is a very flexible representation. And so when people do something like here, for example, when the person puts something in an object, a thing, but they wear glasses, then we see this happening, this action happening, then we can update the scene graph. And then the robot can do the same. And essentially people and robots can kind of work off the same scene graph representation. Just some small examples there. Okay, so then beyond that, it's not enough to know kind of what's where, but also kind of understand activities. And so here's our early work in the space, from RGB video to kind of a 3D interpretation plus semantic interpretation of what's going on here. Using that in scenarios with smart glasses. In a training scenario, we're supposed to learn how to do a particular task, like here switching out the cartridge. It would be able, which initially was not the case with HoloLens, it would have these very nice tutorials, mixed reality tutorials explaining you a procedure. It would have no idea if you are following the procedure or not. And in particular, afterwards, it couldn't check if you were actually doing things properly. So with this type of actual understanding, we essentially here following along, and if you do something out of order, so it would actually detect that and it would warn you. And then following on that, we try to then collect a more a larger data set. So here we had a data set effort again, where the scenario is you have a remote person that explains to a person on site what they are supposed to do. So they explain them the procedure. So for example, here it's switching out some stuff on a game console. And then some people actually are familiar with that and do it very quickly and with only high-level instructions. Other people might not be familiar with the device, need more detailed explanation of what's where and how to do it, and so on. And so that was really what we're interested in, is kind of this there's different levels of explanations, also corrections, all of this, and we captured all of this, about 200 hours of this, with full multimodal data capture, so 3D scene, video, hand tracks, so HoloLens extract hand tracks, gaze, so there's always gaze also, so we know what the person is looking at. We have the full conversation, it's all annotated. It's also annotated with essentially, does the person make a mistake? Do they do this? So it's all kind of also, we had a company annotate all of it. So this data set is available for those of you interested. Also, you can see that a lot of that could actually be used also for robotic learning potentially. Here's another data set. This was just accepted for the NeurIPS as a data set paper. You have both exo views. Here 9 Kinects, so they all have depth. We have a full 3D pose and gaze and hands and all of that extracted. We have the ego view. You can see here also the alignment. Everything is aligned in 3D. We even have instrumented some of the tools. Also there again for, this can be useful also for robotic learning, this kind of data set. It's about 30 hours of data here in this particular environment. And so, for example, if you're chopping something, you will have the knife will kind of nicely register that with this IMU. Building on that, we've, together with Siu Tang, my colleague at ETH, we essentially build a multimodal kind of model there that links those different modalities from RGB to depth frames to camera trajectories to gaze dynamics, so that, for example, given an incoming video, when you don't have eye tracking, we can actually predict still where the person is likely to be looking for this. Then we're doing more things in this space. We actually are lucky at ETH to have this kind of supercomputer at our disposal. It's actually the Swiss supercomputer managed by ETH. We ended up somehow having 10K H200s to work with. One of the things we did in collaboration with others is build, essentially is build foundation, both world models as well as action models and so on in this space. So that's an ongoing effort. Here's kind of one of the first things we did. It's a big collaboration. Mostly Alexandre Alaï was, let's say, the main driver there, but lots of others of us involved there. With essentially building a world model mostly focused on driving. We'll probably hear much more of that from Wave. So just very briefly, from an image, we want to generate the future through the world model, but we want to be able to steer that. Let me quickly go through this. We want to both be able to steer where objects are going, where what objects show up, what people do, etc., so that we can generate whatever scenarios we want, also change trajectories. So let me just show you kind of how this works, or examples of this. So for example, at the bottom there, you see we have a motorbike that starts at the green position. We can essentially enforce the generated video to have the motorbike a second later or 2 seconds later show up at the blue place, so we can actually force a lane change in the generated video. Same with the object. You see there the car here. We can say we want the car to take us over, like to show up in a few seconds. Sorry, here, oops. Okay, I was not playing this right. Well, okay, whatever. So the car, you saw it's kind of showing up. We can also steer the trajectory, so we can ask the car to go right, or we can ask the car to go left. Here. Okay, something's not working. That's fine. With humans, same thing. We can have the human decide that it should cross the street. Or we can also have the pedestrian just kind of hang around on that side of the street and not cross the street. So we can steer all those things in the generation. We can choose how to influence things. We also generate depth at the same time as another modality, actually pseudo-depth. We've also extended it to be able to generate other types of videos with the same, based on the same kind of model, both egocentric as well as drone videos specifically. Okay, now up to affordances. So on the one hand, we've also on some kind of three-dimensional kind of databases, we've made a lot of work on annotating, making data set to annotate so that we could enable learning, annotate affordances. So we have here a hook pull, for example. with this, the motion then of this will actually have this hinge here, and this corresponds to the action of opening the fridge in this example, and many other things like switching on lights and turning on radiators and other things like that. So many scenes annotated. We've also started this kind of ongoing work where we, from a video sequence, essentially just observe all those interactions and then annotate the scene as we're doing that, detect all of these kind of affordances and possibilities to interact with the scene, as you see illustrated here. We also felt for robotics, it's really important to not only have the visual signal, but to also learn to understand the forces involved. And so what we did was a quite ambitious project of collecting data with both from an egocentric person perspective. So there's a lot of ambition in robotics to be able to learn from examples from humans, because that's what would scale in many ways the easiest. There's also simulation, of course, but let's say in real data, if you can learn from a human, that's much easier to capture and to find online lots of data than if you have to do it from an actual teleoperated robot or so. So what we did here was to both have just ARIA glasses, a person wearing ARIA glasses, opening here this particular dishwasher. Then the same thing, but with the person instrumented with also a camera mounted here at their wrist. Then UMI, the person actually interacting with the scene with the UMI gripper, which is a standard gripper used in robotics for this type of collecting data. It's easier to manipulate the gripper than to actually teleoperate a robot. So here with the gripper, which has also sensors and so on. But then we build our own kind of, a little bit based on the Aloha gripper that's used a lot in robotics, but we did a kind of Franken Aloha gripper in a sense. We mounted, as you can see here, we mounted ARIA glasses on top of it. So the person wears ARIA glasses, but there's also ARIA glasses here. There's an additional stereo camera mounted. A Z camera. We actually have tactile sensing in the gripper, and we have a force torque kind of plate that connects to the handheld thing and the gripper, and the gripper is actually electrically activated. What you don't see, or you kind of see it here, is there's actually quite some cables here, and the person has to wear a backpack for storing all the data that we collect here. But what we ended up doing is we get a good connection to IKEA. And so to collect lots of different environments, we went to our local IKEA store where we had a deal with them that we could even bring our robots. So some of those things were also actually done by teleoperating a robot, but that was a lot more painful, and we didn't do that exhaustively. But essentially, all of this was collected of hundreds of different kind of interactions. I think we have 700 different kind of objects that we have manipulated. Many types of things, but in particular also all of this is augmented, as you see here, with the forces involved. Not just the force at one point in time, but actually the whole curve of the force. For example, a dishwasher, initially you have a lot of resistance, and then once you pull it open, it's much less resistance. Or current robot, if you don't pay attention, it would actually fall over because it's not super stable on its wheels. So it's things like that actually really important for embodied robotics to not only have visual signal, but also augment that with force sensor. Our ambition is, that's not yet done, but our ambition is going to be that with all the data, the rich data we collected here, we can eventually learn to predict from a weak signal like this one, learn to predict all the richness of these sensors. So that's really our ambition. And that would then be a huge, ability to take all of these limited kind of egocentric human data and transform that or predict kind of all of these additional signals that are important to robotics for this. Okay. Here's some examples of things we've done kind of with our robots. So here, for example, we scanned lots of different light switches and focused on that and had the robots be able to then autonomously be able to switch on and switch off the lights. And also actually in our scene graphs, once we switch the light, we also check which light actually went on or off if there's multiple lights in the environment, things like this. Then here's some work in collaboration with Stefan Leutenegger, where we also train from egocentric data and essentially try to reconstruct in 3D the trajectory of the grasp. And this only works for relatively simple grasp, but essentially by predicting, then being able to afterwards predict the trajectory based on what we've learned from Ego 4D, you can then have robots essentially predict how they should manipulate certain objects based on the visual signal. That's what you see here. And then we've done that cross embodiment. So here the same model can also then predict for another robot how to interact with the scene, because it just predicts this kind of the motion. And as long as the gripper kind of goes there, grips, and then executes the predicted motion, this works. Here are a few more examples for this. And then also something that's ongoing here is kind of same thing. So starting from these kind of scenes, but a little bit more complicated manipulation interaction. What we do is is the image encoder. We essentially fine-tune the image encoder to not only that's used in VLAs or so. We have it fine-tuned so that it becomes better at predicting which are the grasp points. And how do we get the grasp points? Well, a video like this here, where you have grasped an object, we roll it back in time to before you grasp the object. And then from that before image, which is typically the image that you would use for visual language action model, the kind of initial input video when you haven't grasped anything yet. From that initial frame, we learn to predict the two grasp points that we observe at this point in time. Okay, so we predict them forward from the initial frame, and so we make sure that we fine-tune our representation to be good at that. And by doing that, we essentially see significant improvements by leveraging that modified image encoder for the VLA. We see significant improvements in, okay, so let me switch to the experiments here, in the kind of grasps and in carrying out the task. So this is here with the goal, not just a simple gripper, but actually a fully articulated hand. So this is actually a hand built by one of my colleagues at ETH, Robert Kachman, that we work with. Here carrying out some of those tasks. So we've essentially fine-tuned Dino to do a better job at kind of being able to predict these grasp points. And that essentially improves significantly the results. So that was it essentially. Here's just kind of some of the kind of things we're doing more in robotics. Last week we had this huge hall here dedicated to at ETH. In the center of Zurich, we have this gigantic hall that's like 50 meters by 20 meters by like 10, 15 meters high. That's essentially has all the robotics group working together. In particular, we've built a whole flat there. Here you see our latest robot and our multiple robots essentially here doing things, and as we are collecting data and things like this in that space, kind of some of the ongoing efforts there. Okay, so that's essentially what I wanted to talk about. So it's about AI in the physical world to assist people and enable robots to get stuff done. And I'll leave you to read these things here, but lots of challenges ahead.
Thanks, Marc. Excellent presentation.